in your class? Starting then. I'm getting no response from you.
Okay, sir.
Achha. Is it visible to you?
Yes, sir.
Okay. Then let us proceed. Okay. Now, the title of the experiment is any more is want to join or not? Okay. Okay. Just wait for 1 minute. I'm coming back. The title of the experiment is Performance Study of a Long Transmission Line. First of all, the theory regarding long transmission line has already been covered, probably in an earlier class, earlier semester, okay, or maybe during this semester. You know the basic equations and you know the basic response, steady state response of a transmission line. When a long transmission, what is a long transmission line? I think it is clear to you. When a long transmission line is excited by a voltage at one end, usually we call it the sending end, then what response we get? Response means the voltage current, usually. What we get at the receiving end, when the line is differently loaded in different manner, what type of response in the receiving end voltage and current, etc. The theoretical idea you have already got. Now let us, through this experiment, let us just verify that. This is the main purpose of this experiment. Objectives, purpose or objectives. To study the performance of a transmission line and observe the values of sending end voltage Vs, receiving end voltage Vr, and sending end current Is. You see, the receiving end current IR is not present here just because of the fact that IR is directly obtained from the loading of the line, load connected at the receiving end. When VR is available, we can always have the receiving end current. So these three quantities we are going to find experimentally. We are going to find these quantities at these four conditions. First one is receiving end is loaded with a resistance equal to surge impedance of the line. Right? I think surge impedance surge impedance, the meaning of surge impedance, the implication of surge impedance is already known to you. You are aware of surge impedance of a line. When the receiving end is connected to a load which is less than SIL of the line. SIL means surge impedance loading of the line. Though I shall very briefly just mention these three quantities, surge impedance, SIL, these two quantities. Uh, when the receiving end is connected to a load which is more than SIL of the line, when the receiving end is at no load condition. Now, I think you have some idea, or you can expect what type of receiving end voltage you will have when a line, when the when a resistance equal to surge impedance is connected at the receiving end of a line. Actually, when a line is loaded with a resistance equal to its surge impedance, the line is loaded by the surge impedance loading. A power transferred to a load, resistive load, whose resistance is equal to its surge impedance, is called SIL. That means in the first section, first part, we are actually loading the line with SIL, right? In the second case, the line is loaded with less than SIL. In the third case, the line is loaded with more than SIL. And in the fourth case, the line is at no load condition. When the line is at no load condition, when the line is at no load condition, what do you expect? I think you have an idea. A long transmission line is supplied at the sending end and the receiving end is open or at no load condition. What voltage we actually expect at the receiving end? Can anyone say?
But here Ferranti effect will occur.
Then what will happen to the
Because
receiving end?
receiving end voltage will be greater than the sending end
The
voltage.
magnitude of the receiving end voltage will be greater than the
Greater.
sending end voltage. The reason that can easily be explained, and I hope you already
Yes, due to
know that.
capacitor present
Capacity,
capacitance, shunt capacitance.
shunt capacitance of the line, right?
Yes, sir.
Now, at the no load condition, the current drawn by the shunt capacitance of the line makes the current delivered by the sending end almost fully capacitive, right? So the capacitive current flows through the line. The series inductance or inductive reactance of the line is comparatively much less compared to its shunt capacitive reactance. So the line effectively becomes a capacitive circuit, and ultimately at the receiving end, you can verify with the vector diagram, receiving end voltage magnitude will be larger than sending end voltage. In the first case, when the receiving end is loaded with SIL, loaded with a resistance equal to surge impedance of the line means loaded with SIL. Okay. When a line is loaded with its SIL, then what type of voltage do you expect at the receiving end? What type means what magnitude of voltage with respect to sending end voltage, what do you expect at the receiving end? Do you have any idea? Actually, when a line is loaded with its SIL, then the receiving end voltage magnitude will be exactly equal to its sending end voltage magnitude. Remember it. And the reason will also be clear to you very soon. In fact, what happens, we are considering a long transmission line, and that means distributed parameter line. Then we, in some occasions, we may be interested in finding the voltage at every point on the line throughout its length. Or we can be interested in finding the voltage at different points on the line along its length. Then interestingly, at SIL condition of a line, along its length, the line will have a flat voltage profile. That is, at every point, starting from the sending end up to the receiving end, at every point on the line, the voltage magnitude will be same, a flat voltage profile. This happens when the line is loaded with its SIL, right? And when it is loaded with less than SIL, the receiving end voltage magnitude will be somewhat higher than the sending end voltage magnitude. When it is loaded by more than SIL, the receiving end voltage magnitude will be lower than its sending end voltage magnitude. So just remember these ideas, and we then go to the next slide. Here it is defined what is surge impedance. Actually, characteristic impedance, this is characteristic impedance denoted by ZC. This is the standard nomenclature. This is by definition, you know, this is ZC, the characteristic impedance of a line. If we now consider a lossless transmission line, that means series resistance of the line is almost zero, negligible. Shunt conductance of the line is almost negligible. In that case, assuming R approximately equal to 0 and Z approximately equal to 0, ZC is reduced to this. This is called, this will be denoted by ZS or called surge impedance of the line. So there is a subtle difference between actually characteristic impedance and surge impedance of a line. Though in analysis, instead of characteristic impedance, we frequently use surge impedance of the line to study various characteristics or performance characteristics of the line. It is obvious that R is actually, for a practical line, R is quite small compared to its series inductance. G is quite small compared to its shunt admittance, capacitive admittance, right? In that case, a practical line can also be very, very closely approximated by a lossless line. Now, why it is called surge impedance? Actually, this term has come from the fact that when we have to do surge analysis of the line, that means the line is experiencing a very high frequency signal, high frequency voltage current. In that case, if you look at the expression of ZC, this omega being very high compared to the power frequency, then this will be very, very large compared to R, and this will be very, very large compared to G. So at that condition, actually ZC coincides with ZS. And at that condition, the characteristic impedance is called surge impedance. This is the reason why we call it surge impedance. Okay. But anyhow, as the R and G is usually quite small compared to uh, omega C and omega L of a line, for all practical purpose, we can use ZS for the analysis of a line instead of using ZC. This makes the analysis somewhat easier, but give us the main result or main concept on the result or concept on the characteristics and performance of the line. Surge impedance loading, as I told you earlier, this is by definition, this is receiving end power with ZS connected at the receiving end. In that case, if VR is per phase voltage at the receiving end, ZS is the surge impedance. Okay, though this magnitude symbol is not required, ZS, if you see ZS root over L by C, that means no complex part. So ZS itself is a resistive quantity. So the surge impedance is a resistive quantity. Okay. So this is actually resistance. This magnitude is just meaningless. VR square by ZS into 3 means 3 phase power. This is by definition SIL. That means the power delivered by the line to a resistance equal to its surge impedance. This is called surge impedance loading. Now, if VR in kV and Z is in ohm, then SIL will be in megawatt, because here we have VR square. The SIL is also called natural power. These quantities have been covered in your theory part, I suppose, but just for recapitulation and ready reference, I am mentioning them. Now, one interesting thing you can observe here, the Q inductive is equal to I square omega L. That means Q inductive means reactive, inductive reactive power consumed by a line, I square omega L, where I is the current flowing through the line. Omega L is the series reactance of the line. Q capacitive, that is the shunt capacitance absorbing the reactive power, or reactive power absorbed by shunt capacitance, that is obviously V square, V being the operating voltage of the line, V square into omega C. If at any condition Q inductive is equal to Q capacitive, that means I square omega L is equal to V square omega C, then from this V square by I square is equal to omega L by omega C, or V by I is equal to root over L by C is equal to ZS. What does it indicate? That means when the line is loaded by its surge impedance, a resistance equal to its surge impedance, then there will be no deficit or surplus of reactive power in the line. Actually, what happens in that situation? You see, for a long distributed parameter line, just imagine a distributed parameter line. Then at every infinitesimal length of the line, we can assume some series inductance and shunt capacitance. Or at every point on the line, we can assume a series inductance and a shunt capacitance. Right? So at every infinitesimal length of the line, some inductive var is being absorbed by the line. Okay. If current flows through the line, of course, and at the same infinitesimal length, some capacitive var is being absorbed by its shunt element. If these two are equal, then at every infinitesimal length of the line, there is no surplus of reactive power. The reactive power, okay, here another point has to be mentioned. Now, shunt capacitance is absorbing capacitive var. Okay. When it is absorbing capacitive var, we can also call that shunt capacitance is generating or delivering inductive var. Right. Absorbing capacitive var is same as generating inductive var. So capacitance absorbed capacitive var, or alternatively we can say a capacitor generates inductive var or delivers inductive var, right? That means at every point on the line, the var generated by its shunt element is being exactly being absorbed by its series element. So at every point on the line, there will be no deficit or surplus of reactive power. Then what will happen? No reactive power is flowing through the line from any point to another. Just think at every point on the line, the var being generated is being exactly absorbed. So there will be no var flow from any point on the line to any other point. Now tell me how var flows through a line, how var can flow. Actually, flow of var requires voltage magnitude difference, right? Between 2 points in a network, if there is voltage magnitude difference, then var will flow from one point to the other. It will flow from higher voltage to lower one. Var means inductive var. Okay. Now, no between uh, any 2 points on the line, there is no var flow. So there is no voltage magnitude difference between any two points on the line. Right? So what we are getting? We are getting a flat voltage profile along the length of the line. Okay? That means from sending end up to the receiving end, between any 2 points, there is no var flow and we have a flat voltage profile when the line is loaded with its SIL. Clear? Now let us gradually approach to our actually lab session. To perform this laboratory, this type of long transmission line, this represents infinitesimal sections of the line having series impedance or series inductance, shunt capacitance. So a long transmission line consists of large number of such elements, series inductance, shunt capacitance, right? Here we have taken a sample, a line 400 kilometer, 400 kV, 50 hertz long transmission line. The inductance and capacitance per unit length here per meter per meter per phase are given. Resistance, conductance, etc. are neglected. Now, actually this experiment or simulation has been done in MATLAB Simulink, right? In the laboratory, the development of this experiment in this short time was not possible. A Simulink simulation has been done to show you the effects. This is a long transmission line and it has been simulated by Simulink. 400 kilometer length of the line, 2 kilometer long pi model, 200 kilometer long pi model, 200 kilometer long pi model. These two have been considered in cascade to simulate the 400 kilometer long line. A source of 400 kV line to line, and you can connect the load according to the situation. And in this experiment, what you will do, you will have to fill up this. First of all, you will have these values obtained from the experiment of simulation, and again you will calculate the values because the line parameters are given, loading conditions are given. From that you can calculate the theoretical values and you will have to verify or compare these, the experimentally obtained result and your calculated result, right? Again, remember, calculated result means you will calculate it from the line parameters. You have the line parameters, sending end voltage you know, receiving end voltage uh, you can calculate if the loading is given. Okay, the same thing will have to be done by you in your calculation, and all these quantities you will get from calculations and you will verify them. This is the table for say run 1, run 2, run 3, etc. For run 1, in run 1 this is the simulation of the line, and load connected is a resistance which is equal to ZS. That means it is loaded by its SIL, or connect resistance at the receiving end whose magnitude is equal to the surge impedance of the line. This is done, and from the Simulink model, the meter readings have been obtained in this way. You see sending end voltage line to line, RMS value in kV 400. Receiving end voltage obtained is also 400. Why? This is the SIL condition. As I told you, the sending end voltage magnitude, receiving end voltage magnitude will be same. This is the sending end current. Actually, this is RMS. Typing error has occurred. This is IS RMS in ampere. sending end current. You see, receiving end current you can calculate, because the, oh, again one thing, you will have to first you will have to determine the surge impedance of the line. Now the line parameters are given, inductance, capacitance are given. You can calculate the surge impedance of the line. If required, you can calculate the surge impedance loading of the line, because 400 kV line it is given from the definition. If you take the line to line voltage, then VR square by ZS, or if you take the phase voltage, then VR square by ZS multiplied by 3. That will be surge impedance loading. So first determine surge impedance of the line, right? In the simulation, that resistance was connected, and this value you will require for your calculations, right? You will get the current sending at power factor. It is given per phase, okay? Per phase sending and power factor. Here you see, if you calculate from these values, receiving end voltage, sending end, receiving end current, etc., or surge impedance loading value, if you calculate, you will get that per phase surge impedance loading, or this multiplied by 3 will give you the surge impedance loading. It is expected, it is almost close to 600, okay, megawatt, isn't it? If you multiply it by 3, it is almost 600 megawatt. And it is quite expected value for SIL of a 400 kV line. This is quite expected value of a 400 kV line. And again, one thing you must notice, that surge impedance of a line is independent of its length. Okay? For a 400 kV line, surge impedance loading is frequently 550 megawatt to 600 megawatt. It is close to 600 megawatt. Sending and reactive power per phase. Now, if the line is loaded by a resistive load, when it is loaded with SIL, that means a resistive load is connected at the receiving end, the resistance being equal to its surge impedance. When it is loaded with resistive load, that means the receiving end doesn't have any reactive power, but the sending end has got some reactive power, right? Now, just you tell me whether this is correct. It is showing some small amount of reactive power. Can any one of you tell me whether this should be correct? This is correct, or this should be 0? Can anyone say? Can anyone guess? Should I give you the answer? Now, no response from you. Yes, students, just give me a response whether I shall tell you or you will try to give me the
Sir,
answer.
please tell the answer.
Actually, just simple. You see, if no reactive power surplus is there, that means at every point the reactive power generated by the line is being absorbed by the line at that point itself. That means sending end will, or sending end also doesn't have to deliver any reactive power to the line, isn't it? Again, see, remember, line itself generates inductive power, right? Because of its shunt capacitance. Shunt capacitance absorb capacitive power. We can say that shunt um, elements of the line is generating inductive power. Okay, the inductive power generated by the line, so the line is generating inductive power. The line is absorbing the inductive power also because of its series inductance. Now at every point, the bar generated by the line or generated by its shunt element is being totally absorbed by its series element. So there is no question of any bar flow. So the sending end will not have to deliver any bar. The reactive power ideally should be zero. However, this is because of some numerical calculation, some error. It is zero, but you can note that this value is very almost negligibly small compared to its active power. Where it is 197 megawatt, this is only 59.6 watt. So this is almost zero just because of some limitations in numerical calculations, truncation, precision, etc. Instead of zero, we are getting this. But ideally, it is zero. In your calculations, mm, you will you may get almost a value like this or somewhat smaller than this. That will depend on how much decimal points points after decimal you are considering. Anyway, this is not a matter of much concern. Power factor at sending end, no reactive power. So it is expected power factor at the sending end is 1 unity power factor. This is almost 0 compared to this. So unity power factor you will get. Phase angle at the sending end, as it is unity power factor, phase angle at the, oh here, actually this phase angle means power factor angle at the sending end. Power factor angle means the angle the sending end current is making with the sending end voltage, right? So sending end power factor angle. That means the angle made by the sending end current with the sending end voltage. This is again almost zero. This should be zero because power factor is unity. So we have got expected results, and this is not any strange thing. This result should be obtained if the simulation is properly done. Then we are coming to run to when the line is loaded by less than SIL. 300 megawatt load is connected, right? The same line, same supply, 300 megawatt load is connected. Okay. Obviously, 300 megawatt is less than SIL because SIL is almost 600 megawatt. Okay. So what we expect? You see, the receiving end voltage magnitude is larger than sending end voltage magnitude. Loading is less, therefore the sending end current is also, magnitude of the sending end current is also less compared to the previous case. Sending end active power, it is again less than the previous case. 300 megawatt is the load. Sending end power is delivering, you see, 345 megawatt. If you multiply it by 3, this is 345 megawatt. That means 45 megawatt is coming in form of line loss. If 300 megawatt is drawn at the receiving end of the line, sending end must deliver, oh no, just I am not telling the correct thing. Actually, due to the simulation result, what is happening? We are considering lossless line. That means sending end. This is again some numerical, due to numerical problem. This should be 300 megawatt, but it is coming 345 megawatt sending and active power. Later I will check, because the simulation initially I didn't check. Others have done it. Later I will check again. This ideally should be 300 megawatt, remember, because of numerical limitation of the simulation. This has become slightly more, 345 megawatt. Sending and reactive power, the interesting point to note, sending and reactive power here is minus. Do you have any idea about the implication of this minus sending and reactive power? Minus indicates capacity. Actually, sending and reactive power, when we call sending and active power sending and reactive power, actually we mean the active power delivered by the sending end to the line, reactive power delivered by the sending end to the line. Here in the meter reading, what we are showing is the sending and reactive power means the reactive power being delivered by the sending end to the line. Okay? Or the reactive power, sending, okay, delivered by the sending end to the line. It is minus means sending end instead of delivering is absorbing reactive power. Right? Absorbing reactive power. Just I shall now tell you something that if you try to remember, that will be better. In power system parlance, actually reactive power is considered as inductive reactive power. VAR is considered as VAR or inductive power. Okay? Now, that is positive VAR or negative VAR. That is, positive VAR is inductive VAR, negative VAR is capacitive VAR. Right? That means sending end here is absorbing VAR or delivering capacitive VAR. Actually, what is happening according to power system people, we do not consider separately as inductive and capacitive VAR. We consider simply VAR. VAR means inductive VAR. Whether it is being delivered or being absorbed, whether it is being generated or being consumed. In that sense, remember transmission line series element absorbs VAR, transmission line shunt element delivers VAR. Or you can consider inductive var as positive, capacitive var is negative, right? Series inductance is absorbing positive var. Shunt element is absorbing negative var. Absorbing negative var means delivering var. The same thing is happening here. Sending end is delivering negative var. Actually, sending end is delivering capacitive var, right? Or sending end is absorbing inductive var. Sending end is absorbing positive var. Sending end is delivering negative var. Why? When the line is loaded by by less than SIL, the var generated by the line or the shunt element of the line is greater than the var absorbed by the series inductance of the line. Okay, series inductance is absorbing var because of current flowing through the line, through its inductance. Shunt element is generating var. Now the var generated by the shunt element is larger than the var absorbed by the series element of the line. Then where will that excess var go? Okay, var cannot vanish. The excess var generated by the shunt element of the line should somewhere be consumed. The excess var then equally goes to both sending end and receiving end. Half part goes to receiving end, half part goes to sending end, right? That means sending end in that case will absorb var. That is why it is negative. When you will calculate the receiving end reactive power, okay, then you will see that the receiving end will absorb some var also. Accordingly, the receiving end power factor. Anyway, in that case, power factor at the sending end, what will happen? It will be less than 1 because of the presence of the reactive power. Our phase angle in that case is, that is power factor angle at the sending end. The power factor is leading. That is the angle made by the sending end current with the sending end voltage. This is positive, means sending end current is leading. As sending end is absorbing var or sending end is delivering capacitive var, obviously sending end power factor will be leading power factor. In the third run, the loading is greater than SIL, 800 megawatt. In that case, just opposite you will observe. The receiving end voltage magnitude has become less than sending end voltage magnitude. Because of more loading, the current magnitude has increased, right? Sending end active power is more because the loading is more. Sending end reactive power is this. Power factor at the sending end is again somewhat less than 1. And this is in this case, now what is happening? Power factor angle at the sending end is minus. That is, the current is now, sending end current is now lagging the sending end voltage. That is inductive power factor. In this situation, what is happening? As more current is flowing through the line, series element of the line, more inductive var is being absorbed, or more var is being absorbed by the series element of the line. Clear? Now the shunt element of the line delivers or generates more or less a constant amount of var, because I think you have observed the var generated by the shunt element is proportional to V square, right? It depends on the operating voltage of the line. The operating voltage of the line remains almost same. This doesn't vary much. So the var generated by the shunt element of the line remains almost same at different operating conditions of the line, upper loading conditions of the line rather. So now previously the var absorbed by the series impedance series element was less than var generated by shunt element. In this case, var absorbed by the series element is more by that generated by its shunt element. Okay. In that case, the var will have to be delivered by the sending end, because this series element requires more var than what it is being absorbed by its shunt element. That will have to be supplied from the sending end to the line. So sending end power factor is now inductive. Phase angle is power factor angle is minus, current is lagging the voltage. Okay, these are the situations. Now at run 4 it is at no load condition. Now no load condition means with this open circuit the simulation cannot be done. Therefore a very small amount of load, 0.01 watt, just negligible almost, uh, open circuit or no load condition. And at no load condition you see, due to Ferranti effect, much increase in the receiving end voltage. Current is much smaller at no load condition. Sending an active power is this much watt, this much watt. These are almost zero. This should be zero for a lossless line. Now because of simulation and numerical different limitations, exactly zero we haven't obtained, but they are almost zero. Power factor at the sending end should be zero. Okay, but a very small power factor we have obtained. Why it is zero? Because the line is drawing fully capacitive current, isn't it? The line is drawing fully capacitive current. Therefore, the angle between the sending end current and sending end voltage will be 90 degree. The current will lead the voltage, sending end voltage, by almost 90 degree, and power factor should be almost zero, and power factor angle is almost 90 degree. These are the simulation results. In your report, this usually your name, roll number, experiment number, etc. will write, draw circuit diagram, write objectives, tabulate results for each run. Tabulate results in the given table and do the following. You will have to calculate surge impedance of the line, and for each run, verify results with theoretical calculations. The results means the results in the meter reading of the simulation you have obtained. These will have to be verified by your calculations.
Sir,
Uh,
here in the can we make a table where two columns, one is the theoretical values and another are experimental were placed?
This
Thank
is just simply no hard and fast format. This is for an idea. You can change the table according to your comfort, your advantage.
Okay, sir.
Side by side, you can keep the column experimental result, calculated result.
Okay, sir.
Okay. Very justify the results obtained in each case. Justify the result means what I have now discussed. From here, you will have to write down the justifications when you prepare your report, and also you have your theoretical notes on this, right? So justification will have to be given for each case, and efficiency and voltage regulation in each case you will have to calculate, right? Not much, you'll have to do that. Now the question, I am then closing this. Okay, the experiment sheet I am closing. Or do you have any question you ask me? Do you have any query? Any confusion? You can ask me.